All right, what we're going to go through here is 13.4, where we're going to investigate the curvature of a curve. So, how curvy is a curve? Is it slightly curved or very, very curved, kind of an idea here? So, let's come up with some ways to actually quantify this. And so, what we're going to do here is the curvature of a plane curve. We're going to call this the rate at which t turns per unit of length along the curve is called the curvature. So remember, t was our tangent unit vector here, and what we're going to do is look at the rate at which it changes. So as we go along the curve, how fast it's going to change. So this page is basically just our little definition of it, and it's just dt ds. So how fast does it change as we move along through the position here? Right here, what we've got is a showing of this, and so what we're really looking at is the comparison of this vector here compared to the next one, and then the next one, and how quickly is it turning? Are we going, as we move along, are we going from this to this? That's a low turning, or are we going from that? Are we going from something like this up to this? Is it turning very quickly? And so that's the idea. We're just looking at how much is it turning as we move along. So if we look at this, we see here we're at this angle, and then as we move along, we're at this, and it's just kind of rotating in that counterclockwise direction there in that picture. Okay, so think of it as like our second derivatives before when we had that kind of thing. Now, we can also do a formula here with dt in terms of dt in terms of our parameter t. And for this, we can start with, we had, oh, that's not a good kappa. We had a kappa on the other page, and it was dt by ds, like that. And we can say that equals dt by d little t, and then this is times dt ds, like that. Well, dt ds, right, because the dt's would cancel, so that's our chain rule. Dt ds is just dt dt. If we change it and make it like this, we do the reciprocal of it, it's ds by dt, and that's just the velocity. So, as a scalar form of that, where this is a scalar, so vector, but the ds is a scalar here, because it's a scalar in our original function here, then this becomes 1 over the magnitude of the velocity, because we're looking at just a scalar, times the dt ds, like that. Okay? And so that's where we're getting this one from. It's just using chain rule to come up with that version of it. All right, and then here we have a straight line that's parameterized by r of t equals c plus tv, so that's just a regular line, for constant vector c, and thus v. Thus, r prime of t equals v, and the unit tangent vector t is v over v. So it's a constant vector, which always points in the same direction, because we're on a straight line, so the same tangent vectors are always there. And it has a zero derivative because it's a constant vector. There's no changing as we move along it. It follows that for any value of the parameter t, the curvature of the straight line is therefore going to be 0. All right, you go through and do this, and it's going to just end up being 0 because, as you can see in this picture, straight line, and every single tangent vector here, they're all the same. All these t's are the same, and therefore that doesn't rotate, and therefore there's no change in t as we move through s or through little t, and therefore it's 0. All right, let's take a look at this example. Here we find the curvature of a circle. We begin with the parameterization. R of t equals a cosine t in the I direction plus a sine t in the j direction. So that is the equation, the parameterized equation of a circle with radius a. Then v, our velocity vector, is dr dt, so we just take the derivative of that. So derivative of cosine is negative sine, and derivative of sine is cosine right there. So these are just the derivatives for the I and j direction. Then what we have here is the magnitude of v equals then the square root of that, right? Take the I component and square it, take the j component, square it, and take the square root. So that's what we're doing there. And so we end up with just, you end up with that sine squared plus cosine squared, which is just a 1, and you end up with the square root of a squared, which is just a, and therefore the magnitude of the velocity vector is just a. All right? So from that, which is pretty interesting because note that was the radius of our circle, from this we find that the tangent vector is equal to our velocity vector divided by its magnitude, which is just negative sine of t, negative sine of t in the I direction plus the cosine of t in the j direction, because what we've essentially done is divided by this and we canceled out those a's right there. And then if we take the derivative with respect to t, we end up with sine t becomes cosine, so take a derivative right there, and you get dt over dt, and the magnitude of it is just equal to 1. Hence, for any value of the parameter t, the curvature of the circle is 1 over the radius, right there. Okay, so when you do that, this 1 over v is a, this happens to be 1 over a times 1 is just 1 over a, which is 1 over the radius. Okay, so interesting little one there for circles. Your curvature parameter is always going to be 1 over the radius. It's independent of the radius of the circle or where you are on the circle, which should make sense because it's not going to change. So we at least would have expected that the curvature was the same the whole way around. All right, taking a look here, the vector dt ds, normal to the curve, always points in the direction in which t is turning. You see that? It's always going to point in the direction that it's turning. So here, as we'd move along from point to point, this would become t, and so t is rotating that way, and that's the direction that normal points. Up here, if we were to move to the next position up, t would be pointing like that, and we're curving this way, and that's the direction that in happens to be pointed. So this is a normal vector. It's going to be normal to our curve because it's normal to our tangent vector. All right. At a point where kappa does not equal 0, the principal unit normal vector for a smooth curve in the plane is that. So that's our regular old normal there, 1 over kappa dt ds. Okay, the principal unit normal right there. All right, and then here for calculating in the principal unit normal, if r of t is a smooth curve, then the principal unit normal is just that, the dt dt over the magnitude of dt dt. And you can see on the previous page that happens because when you plug in kappa, you end up getting stuff cancel out. And this is just, that's right there what you end up with, dt over that. Okay? Because kappa is, right, this kappa is dt ds, right, or the magnitude of dt ds. So that's how we have that divided by there. All right. And that's our normal vector. So let's look here. Let's find t and n for the circular motion. R of t equals the cosine of 2t in the I direction plus the sine of 2t in the j direction. So to find the tangent, right, to find our tangent vector, what do we do here? Oh wait, sorry, I didn't mean to hit that. What do we do? We have to find the derivative of this, right? So our tangent vector, dt ds, is back over here where you just find that velocity vector and then take and divide it by the magnitude to make it a unit tangent. So we take our derivative, t, and that's going to be, so we need t equals dr dt divided by the magnitude of dr dt. Okay, so that's what we're doing here. So dr dt is going to be derivative cosine is negative sine of 2t, but then we have to bring that 2 out in front. So negative 2 sine 2t in the I direction. And then over here we have derivative of sine of 2t, so we need a plus 2 cosine of 2t in the j direction. And then we need to divide this by the magnitude. And the magnitude is going to be the square root of the 2 sine of 2t squared. So 4 sine squared 2t plus 4 cosine squared 2t, like that. And there we go. And so this would then give us our tangent vector, our unit tangent vector. Now to find n, our normal vector, we just need to do this. We need dt, almost like, we're taking another derivative. We're getting into that acceleration range, which tells us the way that our first derivative is changing, and then turn it into a normal. So it's essentially that. We're going to do dt divided by dt, magnitude. And so to do that, you just go through and do it. Just take the derivative of this thing, right? And then go through and divide it by its own magnitude. I'm going to leave that for you to try doing that. But take the derivative of that whole thing, divide it by its magnitude like I did for that first one. All right. Circle of curvature for plane curves. The circle of curvature or oscillating circle at a point P on a plane curve where kappa does not equal 0 is the circle in the plane of the curve that is one tangent to the curve at P, so it has the same tangent line that the curve has the same curvature the curve has at P, and 3, lies toward the concave or inner side of the curve. We'll look at a picture here in just a moment. The radius of curvature of the curve P is the radius of the circle of curvature, which, according to example 2, is the radius of curvature is, we're going to call it rho. That's the Greek letter rho, and it's going to be 1 over kappa. To find rho, we find kappa and take the reciprocal. The center of curvature of the radius, the center of curvature of the curve at P is the center of the circle of the curvature. So when we look here, here's an example. Here's our curve going around there in blue, and then you can see a red circle drawn in. If we were to zoom in on this spot and keep zooming in, what you would see is that this tangent vector is both tangent to the circle and to our curve, and we're all going to have the same values here. And we also have then a radius of curvature that we can sit in there. And so you can do other ones of these, like you might have you might have a circle right here, and you'd have a different radius of curvature here, where you would have the unit tangent like that, and then you would have you'd have the normal vector here pointed toward the center of the circle, where that would be the center of curvature for the radius of curvature at that location. So as you move along, different circles would fit there and kind of tell you, like, how circular is it being at that point? How big of a circle type of a thing is that? Okay, so of course the smaller the radius of curvature is, the more curved it is. The larger the radius of curvature is, then the more smooth it is, the less curved it is, because it's equivalent more toward a very, very large circle. All right, so here, example 4, find and graph the oscillating circle of the origin parabola y equals x squared at the origin. So this is kind of like the one I was just drawing on that. So we can parameterize the parabola. R of t equals ti plus t squared j. And then you end up finding, if you go through and do this, you end up finding this circle that's going to have a radius at 1/2 and everything just like that. Okay? So curvature and normal vectors for space curves. If a smooth curve in space is specified by the position vector r of t as a function of some parameter t, and if s is the arc length parameter of the curve, then the unit tangent vector t is dr ds equals v over the magnitude of v. The curvature in space is then defined to be this. So we had actually already defined this kappa like that. Just as for plane curves, the vector dt ds is orthogonal to t, and we define the principal unit normal to be then this, where we do 1 over kappa times dt ds, which is just dt dt over dt dt, like we're taking the unit vector of the derivative of our unit vector. Okay? So here, example 5, find the curvature for the helix. And here's the actual equation for it. R of t is a cosine t of in the I direction plus a sine t in the j direction plus bt in the k direction, where a and b are greater than 0 and a squared plus b squared does not equal 0. Okay, so this is the same helix thing we've seen before, where it's going to be doing some kind of spiraling, not spiraling, helixing up like that as we go around like this. Okay, so helixing around like that. We calculate t from the velocity vector v. So we have the vector v equals negative a sine of t in the I direction plus a cosine of t in the j direction plus b in the k direction. The magnitude of v is just that. You just square each component, add them all up, and take the square root, so a squared plus b squared. And then our unit tangent is just that velocity vector divided by its own magnitude, and so it's the unit velocity vector. Then we can go from equation 3, we can find kappa, where kappa is 1 over the velocity vector times dt, the magnitude of the velocity vector, times the magnitude of the rate of change of our tangent vector, dt. And so you end up with this right here. Here is 1 over the magnitude of v, and here you take the derivative, dt. Remember, dt included that 1 over a squared. So what we're doing is bringing that down and then taking the derivatives here for each one of those, and that, of course, just goes to the derivative of, a plus 0 in the k direction. So that one's 0. And then you have a over a squared plus b squared equals negative cosine t in the I direction minus sine t in the j direction. And then you end up with that final result there. You take those square roots, cosine squared plus sine squared, that's going to equal 1. And then, because we're doing the magnitude of it, and so you just end up with a over a squared plus b squared. All right, so from this equation, we see that increasing b for a fixed a decreases the curvature, okay? And then decreasing a, so that's the radius of it, of our circle, for a fixed b eventually decreases the curvature as well. If b equals 0, the helix reduces to a circle of a radius a, and its curvature reduces to 1 over a, okay? Because that would be, b would be 0, and you'd have a over a squared, which is just 1 over a, as it should. So good, that matches what we would expect. And then if a equals 0, the helix becomes the z-axis, because we essentially have no radius to it, and you're just going straight up the z-axis at that point. And the curvature, again, reduces to 0 because that's 0 over b squared. Okay? And so, again, that fits as we would expect. Here is a picture of that situation. So you can see the helix going up, but I already drew it. But there it is if you want to see it again. And here, find in the normal for the helix r of t equals that. So the first thing you're going to want to do here is you're going to want to find our unit tangent, right? So we're trying to find, where was our equation? We're trying to find this right here. So we need to find t, then we need to find the derivative of t and divide it by its own magnitude. So let's see if we can do that, or at least get you started on it here. So t, let's start with finding t, is just going to be the derivative of this divided by its own magnitude. So this will be dr dt divided by dr dt. So we want the unit tangent, right? And so that's v, that's v over the magnitude of v, right? That's what we're doing. So the derivative of a cosine of t is just going to be negative a sine of t, and derivative of a sine t is a cosine of t, and the derivative of b times t is just b, and then we divide this by its own magnitude, so this becomes a squared sine squared of t plus a squared cosine squared of t plus b squared. Okay, and we can do some reducing on this, we end up with sine squared and cosine squared. Those are going to give us our 1 if we factor out the a. So we end up with negative a sine of t, a cosine t, b divided by the square root of a squared plus b squared. Make my a squared a little nicer, just like that. And so there's t. And now the next thing we need to do is just find dt, right here, right? Oops, one more page. We need to find dt and divide it by its magnitude right there. All right, so let's go ahead and find that. So dt, like this, is going to be just that with our derivative. So we're going to be doing, we can carry along this 1 over square root of a squared plus b squared and just take the derivatives of each component. Derivative of sine is cosine, so we leave negative a cosine of t. Derivative of cosine is negative sine, so we get negative a sine of t, and then the derivative of b is just 0. So this is what we end up with. And then we have to take and divide that, right? Our unit normal has to be dt divided by the magnitude of dt, like that. So we take this and we have our whole thing here. We've got negative a cosine of t, negative a sine t, 0, divided by that square root of a squared plus b squared. And then we have to divide this by the magnitude of what we had before. And so again, this will be the square root, this time of a, negative a cosine of t, that's squared, so that's an a squared cosine squared. And then this one squared is going to be plus a squared sine squared, right, of t. And then 0 squared is just zeroed, so I'm not even going to write it. And then the sine and cosine, we can factor out that a. It's cosine squared plus sine squared is 1. And you end up with the square root of a squared, which is just the square root of a. So this would just be negative a cosine t, negative a sine t, 0 over a times the square root of a squared plus b squared. And there you go. That should be it. All right, and that's it. That's the end of this section. So, make sure you go through this. If you need to, listen to it all again, think your way through it. But it's not too complicated for this, as long as you can remember how we're defining that curvature kappa, and you can just kind of go through pretty quickly with these. All right, that's it for now. Thanks.